If you've been on the internet recently, you've probably seen the term neural rendering being thrown around. The first time I heard of neural rendering is during the release of the RTX 50 series when Nvidia showed off a tech demo. It looked interesting, but it didn't really explain how any of this actually worked. And until now, there really hasn't been that much new information. So what even is neural rendering? Well, it's a pretty broad term. There are a lot of different types of neural rendering, but they all have one thing in common, and that's machine learning. Typically, games are rendered on your GPU using tons of math, things like lighting, shadows, reflections, textures, and the interactions between all of those all use very complicated math. So if you want things to be more advanced and better looking, you need to use even more complex math. So the idea with neural rendering is, can we do what we already do, but with neural rendering in that same pipeline? So what are the actual use cases? So there is a lot of them. Some you may actually be using today. A very common one now is upscaling. I'm not going to go too deep into it because most people already understand the basics of this. If not, I'll leave my video down below. A better example is with ray reconstruction. Normally, ray tracing is very noisy. To keep games playable, you can only have a limited number of rays per pixel. And to fix that noise, you need something called a denoiser. These are usually hand-tuned, and while they do help, they're not perfect. Ray reconstruction aims to change that. It uses machine learning trained specifically on ray trace data to clean up the image in a much more efficient way. A good showcase of this is in Crimson Desert. This game was designed with ray tracing, which is surprising with how bad the ray tracing can look at times. At 1440p max settings DLAA, in darker areas, mainly indoors, shadows look kind of chunky almost, and reflections also look pretty bad. But turning on ray reconstruction massively fixes all of these problems. The chunky lighting is now gone, and reflections are way sharper as well. But it's not just a magic button. In Crimson Desert, it is extremely taxing for some reason, and I know in this game it forces you to use the max lighting setting, but already in this game, ray reconstruction drops performance a lot more than it does in any other game that I've used it in. In Cyberpunk, the performance hit is much smaller, still with major improvements, especially in reflections. Looking at the new stuff Nvidia is currently showing off for neural rendering, they break it into 3 different categories: pipeline, uplift, and generative. Also, Nvidia did say these are not mutually exclusive, meaning you can use a combination or all of them at the same time. Generative is pretty much exactly what it sounds like, but it doesn't really seem like it's for games, hopefully. Most of what they showed for generative was use cases for autonomous vehicles, and if the future of game development turns into just placing basic shapes and telling AI what to do with it, it's going to be a pretty sad future. The other one, uplift, is where it's a lot more relevant, and this is where DLSS 5 actually comes into play. But what's interesting, during this whole talk, DLSS 5 is barely even mentioned. I don't know if it's because the major backlash it got, or maybe it's just not that interesting compared to the others. One thing I wish they explained is whether or not DLSS upscaling, ray reconstruction, or frame generation fall under this uplift category, because to me, they feel different. They are involved with rendering, versus DLSS 5 is just taking the final rendered color data with motion vectors to provide a subjective graphical upgrade. But the most interesting part by far is the pipeline side of neural rendering. This is where things actually start to change how games are made. One example is NTC, or neural texture compression. The idea is actually pretty simple. Instead of storing full-res textures like normal, Nvidia uses machine learning to compress them into something called latent features. Then a small neural network reconstructs that texture on the GPU. And importantly, this is deterministic, so it is not generating something new. It is just storing the same data more efficiently. Now, if it works like they say, it seems to be better than the traditional methods like BCN, which from my understanding is pretty standard in games. Looking at their examples, they show a Tuscan villa scene. With normal BCN textures, it uses around 6.5 gigabytes of VRAM, but with NTC, 970 megabytes. That is an insane difference. They also show the quality comparison with equal VRAM usage, and NTC is a massive resolution improvement. And what excites me about this is being able to use super high-res textures for around the same amount of VRAM usage as regular textures. They do also claim it will reduce game sizes and will lead to smaller game updates and patches, and this is available for developers to start implementing into their games right now. The next thing is neural materials. Basic idea is being able to use extremely high quality materials in real time. Similarly to NTC, neural materials encode complex material properties into neural representations. They went into a lot lot of detail about this, but it doesn't seem like it's ready the same way NTC is, but still the potential is very promising. But of course, there are downsides. For starters, it could just not work. We probably won't see widespread use of things like NTC or neural materials for a while now. And then I think the biggest issue is vendor lock. Everything I talked about today was from Nvidia, which unless they make it open source, which would be cool, it will probably be limited to just their GPUs. Now, 100% AMD and Intel will have their own versions of it eventually. Intel and AMD have already shown off their versions of NTC. We also don't know how demanding this stuff will be. NTC, I would assume, would be available on mid-tier GPUs, maybe not so much with the neural materials. And with DLSS 5, we already know it at least needs a 5090 in its current state. It honestly could be like early ray tracing where it's just not usable till multiple generations later. That said, I am still really interested in neural rendering. Some parts of it could genuinely change how games are made. Other parts do feel kind of pointless. But that is all I have for today. I hope you all enjoyed. Peace.